Welcome to Study Loop.
So in this situation, we have a particle far away from the sun, and we want to know the residual force that it applies to know what direction of the tail of the comet is pointing at. So at a distance away from the sun, let's call this distance r, capital R. We have the pull of gravity, but also the sun is radiating away, and so there is a radiation pressure exerting a force in this particle that we assume to be spherical. We just need to know each one of these forces and then see when they are combined, when they cancel out, to know the limit between the place where the gravity wins and the limit where the radiation pressure wins. So first, the force of the radiation is just the intensity times the cross-sectional area divided by c. So we are assuming a spherical particle, so the area, cross-sectional area, will be pi r squared. So this is the intensity is the pressure, the power of the sun divided by the distance away. So this is intensity is power of the sun divided by 4 pi r squared, and the cross-sectional area is pi r squared divided by c. So we can just simplify a little bit. So this is power of the sun, radius of the sphere, divided by 4 r squared c. Now the force of gravity is just the Newton's constant, the mass of the sun, mass of this particle divided by the distance away, this r squared. So this is, we can write the mass in terms of the density because we are assuming that is a sphere, and the volume of a sphere is 4/3 of pi r cubed. So this is gms divided by r squared times 4 pi r cubed divided by 3. And we can write this as 4 pi g ms rho. So this, we have a rho here because we are writing the mass as density times volume. Rho r cubed divided by 3 r squared. Now we want to know the at what radius this happens. So let's find out the condition where fr is equal to fg. So let's write both sides. So this is pressure r square divided by 4 r square c, and is equal to 4 pi g ms rho r cubed divided by 3 r squared. So we can find the equation for small r, so the radius of the sphere, to make this work. So this r is equal to 3 times the power of the sun divided by 16 pi c, the density, gravitational constant, and the mass of the sun. And we can just plug values. So let's go to another one. So plug values. R is equal to 3 power of the sun 16 pi c rho g ms. So this is 3 times 3.9 times 10 to the 26 divided by 16 pi speed of light, 3 times 10 to the 8. The density they give us 3.5 times 10 to the 3. The gravitational constant is 6.67 times 10 to the minus 11. And the last one is the mass of the sun. There is 1.99 times 10 to the 30 kilograms. Everything is multiplied here, and this gives us 1.7 times 10 to the minus 7 meters. So now, since for B they want to know if its radius is larger, does the path curve away from the sun or towards the sun? Since FG varies with r to the cube, so r to the cube, and of r varies with r small r squared. If the radius is larger, so if we have r new larger than the r of the equilibrium, this means that fg will be larger than fr. So the path will be curved toward the sun. So because the gravity will be winning, so in this situation we have the sun here, particle here, and the net force will be in this direction, F net.